All right, Brian, you're with Ryan Corporation,
Bryan Company.
Ryan Company, and why don't you tell us, we're down here at the basement of the elementary school in the boiler room, what is the problem we're attempting to solve?
It's not a problem, it's an improvement. We have two boilers that are independent of each other.
Why don't you point out those two boilers?
The electric boiler on the right and the electric boiler on the left, they are interconnected on the steam piping side, but they don't talk to each other.
Okay.
They each have 8 stages of electric elements, and when one boiler on the right is running and the boiler on the left is off, this boiler is pushing steam and it's condensing in the boiler on the left. The controls that we have today are not conducive or built to run two boilers together at one time. So it's not as efficient when we fill up a boiler, then John comes in here and the boiler's full of water, or Roger has to drain the water out. The water's been heated already.
Okay.
So what we want to do is we want to limit how much water is dumped on the floor through the condensate tank into the sump basket, which goes to the floor drain. We don't want to heat up the city's drains. We want to be able to independently run the two boilers together, combining them so they're not independent anymore, through a control that would keep all the safeties where they're at, but it would stage the 16 stages, 8 and 8 together, so we'd be pushing out, they'd be working as 2 cylinders instead of 1 independent of the other one.
You're creating one system.
One system.
Everything works together.
Yeah.
And let's say the district, you know, because this district has limited funds.
Yep.
Let's say it spends 16, 17,000.
Yes.
Where does it save?
The savings will, well, that calculation is, I guess, it's subjective to how much water we're dumping in the drain. It also does outdoor reset. So today in most schools, we're going to talk about steam for a second. In most schools throughout the U.S., this is just part of steam. We can move steam pressure up 1,000 feet vertically or 1,000 feet horizontally and lose 1 pound of pressure. So with that saying, that general statement, we should be running 3 to 4 or 5 pounds of steam. When it gets colder out, we might need a little bit more. When it's warmer out, we might need less. That control would be able to adjust those set points. And as an example, 4 pounds of steam equals 224 degrees. 8 pounds of steam is 234 degrees, which is more pressure and more temperature. And although an electric is a little different, but on a fuel-fired boiler, it's less efficient to push 8 pounds versus 4 pounds. So
Okay, you're talking about the big boiler.
the big blue Kiwani.
Yeah.
So what we would be able to do with this control is to stage these two boilers together. So we're not dumping condensate, lowering the water level in the boiler, which is already heated water and chemically treated water. We would be working those two together. If these two boilers, for some reason, fail, either through your existing system or through this new PLC, it would automatically turn on that boiler. So you would have an automatic system as long as the oil pumps would be running. And we would be able to pick up some alarms from these 3 boilers that could go back to your building management system. So if you have a building management system in this building, or we could have an alarm system set up that we would know, and then we would know if there was an alarm. Then if you do have a desktop building management system, John would be able, or Roger would be able, and I forgot your name? Steve would be able to know how many stages are on each boiler. They would also know what the steam pressure would be.
Yeah.
And then they could remotely run the steam pressure from their desk, doing either a direct, if it's 20 degrees outside as an example, and windy out, or 20 degrees and sunny out, the temperature is technically different on the building. You will need a different load, but having a 4-pound steam set point is going to mean maybe we might need 5 that day, so John or Steve or Roger could go back and make that adjustment from the computer, or come down here and make it on the PLC.
So the management of the heating system would be improved.
It would be improved. You would have less chemicals used because you won't be dumping as much. We could actually possibly tie it into the number of blowdowns. We could actually, if we can get an output from your conductivity meter, we could display the conductivity on your system through the PLC. That would be just a contact into my PLC. And if you had to, you could override it and go back to the old system by going to local control. So there's a couple of different options. But how you're running it today is one boiler comes on, has no idea there's another boiler there, or the big blue Kiwani, we're pushing steam out, and the steam out there is going where it needs to go. Now, the other thing I'm going to do with that condensate tank, Roger and Steve are busy in this building, so is John. Here's a good question for you, all three of us, all five of us. I know the answer, so it's a little unfair for me to answer, but I will. If our condensate tank is running at 160 degrees continuously, but it goes up to 180 on a day, what does that tell us? We have a bad trap. So what I'm going to do is, if there's a well, if not a well, we'd be able to put a surface-mounted sensor on that tank that would go back to the same PLC. It's not going to do anything but give you an alarm saying, hey, your condensate's going up. Well, if it's going up, creeping up, we might not have 5 traps bad, we might only have 1. When you have a bad trap, Steve or Roger or John might come in there and have to boost the pressure up to get that radiator hot. That's the last thing you want to do. The first thing you want to do is fix that trap. Remember, going from 4 pounds to 8 pounds steam. Now, if you have 4 pounds of steam running perfectly all the time, and it goes up to 8 pounds, you have to bump it up to 8 pounds, you're putting 8 pounds of pressure instead of 4 pounds on all those traps, so your longevity of your traps will diminish over time. Quicker. You'll lose your life out of your traps. They're mechanical devices that go up and down, so if you're pushing on it with 8 pounds, it's shortening the life of your traps. So not only would this boiler control help out with your energy, it would also help out with your management of your traps.
What do you figure the payback is? Let's say the district spent $16,000.
Well, I would say, depending on the electric bill, you'd probably have 1 or 2 year payback.
You think it would pay back in 2 years?
It'd be, again, it's subjective to how it's running today, but all the jobs, I'll give you an example of a job we put that same control in. Ridgewater College, we know this job very well. Ridgewater College was spending $96,000 a year. We put that control in, we didn't change any boilers, no piping. We reduced their consumption down to $60,000. So they were spending 60% more than they should, from 60 to 96 is 60% more, and we reduced it 40%, and they like their system. The cycling count went down, so we're not cycling the boilers as much. That control is basically, it's got some intelligence. And once we set this control up, it's not a walk-away control like we did with the boilers. They walked away, they had to come back and make it work, but it's because of the piping and how it's laid out, it wasn't the most ideal system. But they got it to work, but we're going to improve it even more. When I say, are we doing anything wrong? No. We're going to enhance it to make it better. So your glass is always half full.